if I set n equal to 0, then we also talked about how your dance moves work. So when you had your n behaviors with your dance moves, you knew where your zeros went, you knew how things changed direction, things like that. So we kind of just brought all of that with us throughout all the parts, and it wasn't all that terrible. What I want to do today then is to go into it more. We did this one. No, we did. This is easy. And go into stuff like this. Now what do you do? So we'll start with this one. X cubed plus 27. Yes, it is. Today will be the last day of 6-4. Tomorrow we'll kind of review a whole bunch of junk together, and then we'll quiz Wednesday over 6-1 and 6-4. That's kind of what I think I had that on the calendar and all that stuff too. That'll get us 6-5 Monday, or 6-5 will go Thursday, Friday. 6-6 will probably be easy to do for Monday and Tuesday going into the break, and that's where everything just goes really crazy. And all of a sudden, like everything that we've been kind of talking about comes to a head, and it tells you why math matters. So, before we get too far into this one, what would you do if it was this? Can't do that. If I wanted to factor that, what would I do? X plus 3, x minus 3. I would have to factor it because you're asking yourself, is the first term a perfect square? Is the last term a perfect square? Is that a subtraction symbol? And that's how you would factor that. Now, if this was a plus sign, what would you do? You couldn't factor it. All right? If it's a sum of squares, it's not factorable. If it's a difference of squares, it is. Now, when we get to the cubes, then, cube roots third-degree polynomials, you say, we rephrase that, they kind of have the same basic idea. They've got these rules that they have to follow, where you have what's called a sum of cubes, and then we have difference of cubes. Now, in order to tell whether or not something's a perfect cube, you have to know how to take the cube root. You guys all know there's a button in the calculator for that, right? I think it's like math, and it's option 4 or 5 right off the bat, and then just you can take the cube root of any number. Now, a lot of these you're gonna know. Cube root just means what are 3 numbers you multiply together that are the same number that gives you that. So, what times what is 27? Pretty easy. So, this is what we would call a sum of cubes. And just like when you have difference of squares, there was a specific pattern. There's a specific pattern for both sum and differences of cubes. And we're going to talk about those today. So sum of cubes. If you happen to have a cubed plus b cubed, I'm just leaving it in terms of a and b, just to start. And we'll use the x cubed plus 27 as our example. What you're doing here is this. It's going to be a plus b times the quantity, a squared, minus ab plus b squared. And then if it's a difference, it looks ever so similar. A cubed minus b cubed. We get a minus b. A squared plus ab plus b squared. And these are those 2 weird patterns that you've never really learned. Just writing on the whiteboard. So what's the value of a in x squared? Or excuse me, what's the value of a and b for x cubed plus 27? What's your a and what's your b? 3. Okay. It's x and 3. So this one works out to be x plus 3 x squared minus 3x plus 9. And what happens when you have what's called a sum or a difference of cubes, you really only wind up with one real zero. Okay? You're only wind up with usually one real zero, because if I set that equal to 0, I get it at -3, and the other one I'd have to get an imaginary root and do a bunch of quadratic formula stuff. So it's a little bit different. You've seen it. What happens, though, is it just takes time to get used to seeing it more often. For those of you guys that did factoring on a math team test at one point in time, this stuff shows up a lot. Okay? It shows up all the time. That's probably why you're like, oh, I don't remember what that looks like. I'll show you this one. Yeah. Yeah, you're done. Because that's fully factored. That's what it would look like if it was fully factored. Same deal here. If I go into this one, they brought up this during the first hour also. Can you use X and be okay with it? By all means. Textbooks like to change variables on you all the time for really no apparent reason, just to kind of show you that it can be any variable. Just think of it in terms of X's. It's not a big deal. So what I would do when I wrote this down, I would write down 16x to the 5th minus 250x squared. Now, when you look at that, your first rule of factoring is always to do what? GCF. What do they have in common? X squared, is it a 4? Is 4 going to 250 evenly? No. So if it's not a 4, then it's going to be a 2. So if I take out a 2x squared, I get 8x cubed minus 125. Hey, look at that. Is 8x cubed a perfect cube root? Is 125 a perfect cube root? What's the cube root of 125? 5. And usually after that, they try not to make anything too crazy that you couldn't figure out in your head. You're going to see 8s, 27s, 64s, and 125s. More often than not, you'll see some of those. Or with some GCF, some multiplier to that. So you might see, like, what would that be? 128. So you take out a 2, you can get a 64. Things like that to happen. Excuse me. So from here, if I'm going to factor this further, this is a difference of cubes, where A is being played by 2x and B is 5. So what happens here is that as you simplify, as you put them through, usually what students will screw up when you have to square it, when you square that 2x portion, you just write 2x squared instead of forgetting that it's the quantity 2x and squared is 4x. It's the cube root. What's the cube root of 125? I'm looking at what are the perfect cubes out of that. Okay. So if I go through this, then I have 2x squared. I have the quantity 2x minus 5. Then I have 4x squared plus 10x plus 25. And what I'm doing is I'm just following my patterns. Just following my patterns. One nice little trick that you might pick up on is that notice how the signs work with the x squareds and the the sum and the difference. When you have the sum, it was plus between them, so it went plus, minus, plus, and when it was minus, it went minus, plus, plus. So the last one's always plus, the first one's always the same, and then the other one's just the opposite. Okay. Yes, ma'am. Yeah, because you're done. There's nothing, because if you're factoring it, there's nothing left for you to do. Okay. If it's set to do this, then there's something you can do. Are these all, well, aside from this nasty looking thing here, I'd have to use quadratic formula, but could I set that equal to 0? Yeah, I get 2x squared equals 0. I get 2x minus 5 equals 0. Then I get this 4x squared plus 10x plus 25 is 0. Well, what's my 0 here at 2x squared? 0. Here it's 5 halves. And here is that some crazy looking square root thingy with quadratic formula. Yes, Dave? I did. Oh, that's where Ashley was going at. Are you done at that point? This one I was just saying, if it had an equal 0, that's what you would do next. Before it was just, we just factored it and let it go. Okay. Somebody try to song about that. Let it go. Sorry. Let a goat? Or let her gloat? We're coming up with parody songs today, ladies and gentlemen. Just let her gloat. She got them all right, so she's gonna gloat. Or build a boat with the goat. Hope it float. Gotta quit while I'm ahead. Shush. So here's your patterns. All right. Let's factor these two. What on 81x to the 4th minus 16? What are your tails doing? 81x to the 4th minus 16. What are your tails doing? Yeah. They're up. They're up, okay? You didn't. You said down like a frown. No, I didn't hear you. So you know that our tails are doing this. What's your first rule of factoring? GCF, 81x to the 4th and 16. I'm pretty sure they don't have anything in common. So, bless you, there are two terms. So we check and see if they happen to be a difference of squares. I'm not worried about checking to see if they're some are a difference of cubes because it's an even number. So it's 81x to the 4th. What's the square root of 81x to the 4th? 9x squared. What's the square root of 16? 4. Is that a subtraction sign? Good. So you can do this. 9x squared minus 4. 9x squared plus 4. Which means, what can you do? You can't take a square root. Stop saying that. You can't do that. No, it's not. It's 9x squared a perfect square. It's 4 a perfect square. You can go further. But I cannot go any further on the 9x squared plus 4 because it is no longer a difference of squares. It's a sum of squares. That you cannot factor.
Why not?
What times what is 36 you add together to get 0? That would be 12. You get a non-real, you can't factor that. And you're done. Okay? And you're done. If something changes and I ask you to find all of your zeros though, if I say find all zeros, what would you do? Well, I'd be plus or minus 2/3. And then this one would be, well, I would say 9x squared equals negative 4. It would be x equals plus or minus, well, it's going to be the square root of negative 4/9, which is very good. Okay. So you still have 4 zeros, 4 real zeros, or not 4, excuse me, 4 possible zeros. It just so happens that only 2 of them are real. Okay? And that's fine. For right now, we're not worried about any graphing of this one, but we know where real and or non-reals may occur. What about 4x to the 6th minus 20x to the 4th plus 24x squared? What do you think you're going to do first? GCF. Good. Now, one of the things I want you guys to see, excuse me, if I take the GCF out of that, well, first of all, what is the GCF? 4x squared. Good. So if I take my 4x squared out, I'm then left with x to the 4th minus 5x squared plus 6. Now here's the next new-ish part. Whenever you have a trinomial, then that your degrees started an even number and you get cut in half. Factor it like you would if it was an x squared times 5x plus 6. Your factor the exact same. What times what's positive 6 that you add together to get negative 5? Negative 3 and negative 3 would be the positive number. I didn't hear that too. I heard you say negative 3 twice. That's what I thought you said. Okay. So you get 4x squared. We get x squared minus 2. X squared minus 3. And a factor. What's that? Where? Because if you think about it, if you start foiling all that out, I get an x to the 4th, and I distribute it into x squared, I'm going to have an x to the 6th. Now, let's get real crazy with this one. I know. Now, we did one a second ago that had, I think it was a 2x squared out front. We said equal to 0, and it was just at 0. All right. Now, here's what happens. We have a 0 at 0. We have a 0 at plus or minus root 2. And we have a 0 at plus or minus root 3. Everybody okay with that? I just add 3, took the square root, add 2, took the square root, divide by 4, took the square root. Now, in this case here, I only have 5 zeros listed. But here's the weird new thing. Since this part here is a squared term, and 0, it technically occurs at 0 twice. Well, we don't write it down twice. We say it has what's called multiplicity. The term multiplicity means it just happens multiple times. It's a fancy word to say it. It's there twice. So we'll just say it's got a 0 with multiplicity of 2. Okay. If you remember how we talked about tails and dances and how the zeros go through things? If you have a multiplicity, it means it changes, the curve changes direction at that 0. So this one here has 4x to the 6th. That means I'm up, right? Because it's positive and they're even. That means I'm up. I have zeros at 0, negative root 2, negative root 3, root 2, root 3. So if these are my zeros, what happens is by graphing it via the tails, I know that it has to come down through here, come back up. Oops. Changes. It has to do that. My graph has to look like that because it changes direction at the 0. It has what's called multiplicity. It touches there once. Think of your oh god, what is it? It was called like x squared. Bless you. X squared plus 6x plus 9. That's the quantity x plus 3 squared. Junk squared. Junk squared has 1 0. Negative 3. It changes direction at that 0. Okay? So if you look at this graphically then, if I type that in, it was what? 4x to the 6th minus 20x to the 4th. 24x squared. And if I look at that graphically real quick, it does exactly like I just thought it did. Okay? Oh yeah, it did look like a W, didn't it? Tails totally are up, came down through the zeros, came back up because it changed direction, and it touches one time at 0 and comes back around. It's fancy. Okay. It looks kind of like what I have. What's that? A W. Because they're up. If it was down, it'd be an n. All right, 2x to the 5th plus 24x equals 14x cubed. Now, obviously I have, there's a 0, we're going to have to find a 0 here because it has an equal sign. As you write this problem down, why not just put it in descending order as you're starting the problem out? You know what I mean? Automatically, just write down 2x to the 5th minus 14x cubed plus 24x is 0. Now you're back to a, well, what's the first rule of factoring? Yeah. What do we have? 2x? So we factor out a 2x. I now have x to the 4th minus 7x squared plus 12 is 0. So we have 2x, x squared minus 4, x squared minus 3 equals 0. Do I have to continue to factor this the rest of the way? I know that I can factor out the x squared minus 4 and rewrite it, but do I need to? I don't need to because it says equals 0. So if I get to a point where I know I can find my 0 by just saying, oh, that's just going to be plus minus 2, I can do that, right? Because I've got 3 parts that I can set equal to 0. I have 3 parts that I set equal to 0. 2x is 0. X squared minus 4 is 0. X squared minus 3 is 0. Which gives you zeros at 0 plus or minus 2 and plus or minus 3. What are your tails doing? Down up? They're down up? Because it's positive and odd, so they're down up. If they're down up, and you know that you have zeros at 2, -2, negative root 3, 0, root 3, and 2, doesn't it have to do this? It has to. How far or how high up these things go, I don't know. But it has to look like that. There's no multiplicity. There's no repeated zeros there. So it just has to continue through. Your tails tell you what it's doing. The graph, when you have zeros, means it has to pass through those points. Somewhere in between those points, it has to change direction to go back and forth through them. The 5th degree polynomial, and lo and behold, how many zeros did we have? 5. Okay. We want to find them. Take a minute and do these two. And yeah, that's a negative 2x to the 6th. Negative 80. I'm going to try and go down there this week. Can't get them here. Yeah, I'll go pick them up. Debbie, come with me.
I'm forgetting how to do
So, what do you do with that negative 2x to the 6 equals 16? What do you do first? You can set it equal to 0, but remember, you're trying to find a 0. So, wouldn't it just be as easy to divide by negative 2? I can't.
So if I divide by negative 2, and I think we're only looking for real zeros, so that might help to know. So if I divide by negative 2, I get x to the 6 equals negative 8. I don't know about you guys, but I'm not really up on my sixth roots, but I can pretty much sure that 8 is not a perfect sixth. So also, is 6 an even or an odd exponent? It's even. So if I take, can I take an even root of a negative number? No. There's no real answer here. There's no solution for this because there's no real answer for this, because in order to basically take what's called a sixth root, which we haven't learned yet, which is a thing, this number would have to be positive because you're looking for 6 numbers that are the same number that multiply together to get negative 8. Well, if it's a negative times 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 a negative, that would be positive. In other words, not negative 8. So the answer is no. Okay. But on the other one, it wasn't so bad, was it? Did you get that one done yet or no? All right, sorry. Sorry. Does that make sense about why that doesn't work? The textbook today, the problems I have for you guys, you're going to be finding all real zeros, so you don't have to worry about anything that's imaginary, all right? Tomorrow we'll do a little bit of review practice and stuff like that we will have to throw some imaginaries in. And we will throw in a couple ideas of dance moves where how do you graph it via some zeros and stuff. So just kind of all put all this together. I believe you start with that. First rule of factoring. What times what's 8? You add together to get negative 6. And 4, negative 2. Very good. From that, can we list zeros? Pretty easy at that point. We have 0, plus minus 2, and plus minus 1. What would your graph look like? It's down, up. Something like that. No, that's the problem. It just so happened that the first couple examples had 5. There's some that, I've seen some that have like 9. You know, when we start doing this stuff long form, I try not to go with too high of a degree, because as you get going with some of these things, you can get pretty ugly rather quickly. So I try to keep it in some sort of semblance of doing things. Also, what's nice is that the things that you guys are working on today, or these first 4 sections, I should say, the numbers work out real clean. Okay. As we go along, as we get going further into this stuff, you'll have to be able to, you're going to come up with ways, and I'll show you like a hint of how to start it, and then you're going to determine what are your zeros, by using that synthetic substitution. So we go from there. Do you need any more, or are we okay? All right. I think I've got like 12 of these for you tonight, if I'm not mistaken. It was at 68 through 88, but I had you skip a couple of them. Yeah, it was 68 to 84 evens, and then 87 and 88. It's on, forgot page. It's the same page as 6-4. It was the same page. What was it? 349. It's on 349. So those are all. Devin, you have a question? I thought you had a hand up. I was going to say hi, Devin. So we'll work through those, and we'll just kind of put them all together tomorrow and go from there. Okay. So let me see here. So here's the whole thing. If you guys just want to take a picture and work on it. Yes, ma'am. Stop this real quick. I'll be right there. Ladies and gentlemen, you guys have a good 15 minutes. You can get started on this. Let's go.